Okay, students, 4.6, and today we're studying related rates and parametric equations. I'm actually going to split that into two videos. So to begin with, we're going to take on this idea of related rates, and we're going to start just by thinking about this coffee filter you can see on the screen here. What I'm interested in as I make my coffee each morning is for a given flow rate, so a given amount of water coming into this cone, how fast is the radius of the water going to increase? And I was thinking about that this morning, and I maybe started to summarize the problem by this diagram here. So you can see some measurement. My coffee filter is about 10 centimeters with a radius at the top and got a height of about 30 centimeters. And as it fills up, there's obviously some smaller cone of water in the bottom with a height of h and a radius of r. And the other thing I've measured is that the amount of water coming out of my tap is about 100 centimeters cubed per minute. And I guess my question for you is, can we use that information to actually find the rate of change of the radius of water, given we know how much water is coming into the cone? It's a tricky question, and we've not done much like it before, so I'm not expecting you to get a perfect solution, but what I'd like you to do is pause the video and start to explore how you would go about this, and then we'll go through it, and we'll see how good your reasoning was, how close you got. Off you go. Okay, so before we go on to that specific problem, we're going to look more generally at related rates and what this idea is. And as we saw with the coffee example just now, it's that idea of connecting different variables. So, for example, if we're thinking about this cone, we could have a rate of change of the volume of water, dV by dt. We could also have a rate of change of the radius of water, the radius at the top of the cone of water. And we could also even look at the rate of change of the height of water. And all those things we think are going to be connected. You know, the more water that goes in, the greater the rate of change of volume. We're going to think that the radius and the height are going to increase faster, and the question is how. What we're going to do when we're thinking about this is we're going to use this basic idea of the chain rule, which allows us to connect variables. So, for example, what we're going to look at is the fact that we would expect dV by dt to be the same as dV by dx times by dx by dt for some other variable x. And if we can calculate these two things, well then we can calculate dV by dt and relate those rates. So what do we know about the cone here? Well, we know that the volume of the cone is 1/3 pi r squared h, which is fair enough. But then actually we know more about this cone specifically, and I can see some similar triangles here. So if I just take this in cross section, I have a width of 10 and a height of 30, and I have a width of r and a height of h. And because those are similar triangles, what that means is the height is always going to be 3 times the radius. So the height is 3 times the radius, and that allows me to write the volume here, if the height is 3 times the radius, and I substitute this in as 3 cancelling with the third, pi r cubed. And what I've done there is I've reduced this equation in 3 variables to an equation in 2, and at that point I can then calculate dV by dr. In other words, how does the volume change as the radius changes? And differentiating with respect to r on the bottom of my derivative there, 3 pi r squared. Hopefully that's okay with everyone. And then using this idea of the chain rule, dv by dt, substituting r instead of x here, is dv by dr, dr by dt. So 3 pi r squared times dr by dt. And actually, I can, so here, this is great. I've related the rate of change of the volume to the rate of change of the radius. You can see it depends on what the radius is, but I've got an equation that connects both those things. We'll come back to the specific coffee example in a sec, but before we do that, let's also acknowledge that actually I can bring the height in here as well, because dh by dr is simpler, that's just 3 using this equation here. So dh by dt, the rate of change of the height, is going to be the same as dh by dr times by dr by dt. So we have this cancelling effect. So that must be 3 times dr by dt. There we go. Super. So how does this relate to the question we looked at previously? Well, if you remember, what we saw previously was that the volume, the rate of change of volume, was 100 centimeters cubed per minute, and we wanted to work out dr by dt. Well, using our equation that we just came up with, dv by dt is 3 pi r squared dr by dt. And just rearranging means that dr by dt is dv by dt divided by 3 pi r squared. So 100 dv by dt divided by 3 pi r squared. What does that mean? Well, 3 pi, that's going to be very close to 10. So this is approximately 10 over r squared. Let's just sense that for a second. What this is saying is that if the flow rate, the amount of water coming into the cone, is constant, then the rate of change of the radius is really big when the radius is small, and that makes sense. But then it actually slows down as the radius increases. So, for example, if the radius is approximately 3, then the rate of change of the radius is going to be roughly 1 centimeter per minute. And notice that we can take the per minute part of our units from the original rate that we were given. So 10 over r squared centimeters per minute. So this is the idea of related rates, this idea that we can use our understanding of how different quantities, like the volume and the radius of this cone, are connected, and use it to move from one rate to another. So, I want you to have a go for yourself now and see the question underneath. This time we've got a circle and a puddle, and I'd like you to have a little go at working out what is the rate at which this puddle is increasing, the area of the puddle. Pause the video, have a go. Okay, so won't surprise you that the first thing I'm going to do here is just to sketch my puddle. I have the radius, and I know that the area of my puddle is going to be pi r squared, which is super, which I know I'm going to use this. dA by dr is going to be 2 pi r. Just an aside for a moment, hopefully we recognize 2 pi r as the formula for a circumference, and hopefully it's intuitive to us that if we're thinking about, okay, well, what is the rate of change of the area? Well, it's the circumference. And a way of interpreting that is as we expand the radius, we are adding an extra circumference, an extra circumference, an extra circumference onto the circle, and those extra layers of paint, if you like, the extra circumference around the outside is going to gradually increase the area. So quite a neat little fact there. The rate of change of the area is the circumference with respect to the radius. But what are we doing here? Okay, we know that the radius of the puddle increases at a rate of 3 centimeters per minute. What does that mean? Well, the rate with respect to time is dr by dt. So we know dr by dt equals 3, and we're interested in the rate at which the area of the puddle is increasing. So we're interested in dA by dt, which, using the chain rule, must be dA by dr times dr by dt. So it must be 2 pi r times 3, so 6 pi r. And then in the question here, it says the radius is 2, so dA by dt would be 6 pi times 2, just substituting in, so 12 pi, and then putting units on it, centimeters squared per minute. There is my solution. So this puddle, the area is going to increase at roughly, what, 36, 40 centimeters squared per minute. Great stuff. Okay. Let's step it up just a little bit. Have a go at the question on the next page. This time we've got a block of ice. Start with a picture. Calculate your surface area. It's not actually interested in the volume, the surface area. And see if you can figure out how x is going to decrease at that specific point when x is equal to 2. Okay, hopefully you've had a go at this. So you've got your rectangular block of ice. Here it is. We've got x, x, and 5x as our 3 dimensions, which means the total surface area, well, we're going to have the 2 endpoints, so that's 2x squared, and then we're going to have the 4 remaining sides, and each of those is going to have an area of 5x squared, 5x times x. So overall, 20x squared plus 2x squared, 22x squared, meaning that the rate of change of the area with respect to x must be 44x, which is okay. And then what it tells us is that actually the total surface area is decreasing at a constant rate of 4 centimeters squared per second. So relative to time, we know that dA by dt is 4. But a different way of writing dA by dt is that that is dA by dx times by dx by dt, which means that dx by dt is this divided by this. So 4 divided by 44x, or in other words, 1 over 11x. Oh, hang on a second. One thing I've missed, and very important, that we are able to spot these things when they happen. The area is decreasing at a constant rate of 4. So my formula here is not correct. dA by dt equals 4 implies growth because this is a positive value. So instead, we put in minus 4. So it's decreasing. My apologies. So dA by dx is decreasing, it's negative, giving me a value for dx by dt of minus 1 over 11x. It says calculate the rate of decrease of x when x equals 2. So if x equals 2, then dx by dt is minus 1 over 22. And units, x is measured in centimeters and time is measured in seconds, centimeters per second. Let's have just a think about this a little bit. What this means if x is really big, so the rectangular block is really large, then the rate of change of x is going to be small, so it starts to melt slowly. And maybe that makes sense, because actually, even for a tiny change of x, if the thing is really big, the area is going to go down by quite a lot. Whereas if it's really small, in order for the area to decrease by this amount, we're going to need the dimensions, x, to get smaller much faster. So sense check works here, and we're happy with this reciprocal form. Okay. Hopefully that's giving you the idea of these questions, and in fact, in the exercise you'll see most of them now match the form of the three that we've looked at. But what I wanted to do is just at this point introduce a bit of content that is going to come up later in the course, because it's really closely related. And it's about a special case for when we can do these related rates with displacement, velocity, and acceleration. Because we're used to a form for acceleration, right? Which acceleration is the rate of change of velocity, dv by dt, this here. But this idea of related rates allows us to come up with new forms of writing the acceleration, which can actually help us solve questions. So, for example, dv by dt, we know using the chain rule, is the same thing as dv by dx times by dx by dt. But dx by dt, well, that is just the velocity, the rate of change of displacement with respect to time. So here is another simple way of writing acceleration. It's the velocity times the rate of change of velocity with respect to distance. Then this kind of a different way of doing it, and a little bit of a roundabout method. If I give you a half v squared and ask you to differentiate that with respect to x, well, using the chain rule, I can differentiate it with respect to v. And then I can multiply by dv by dx. Well, a half v squared differentiated with respect to v is just v, because I multiply by the 2, it cancels with the half. So this is just v dv by dx. And that is the acceleration, we've just found that. So actually, this is our second new version for acceleration. So acceleration equals, and we've got three methods, dv by dt. We have 2, v dv by dx, and we have 3, the derivative of a half v squared with respect to x. So here I now have 3 different ways of calculating the acceleration depending on what information I've given. So in particular, if I'm given a connection between v and x, well, then I can start to work on this. And so I'd like you to have a look at the final example just for this video, the one just underneath, using alternative forms of acceleration. See if you can find a relation between v and x. Okay, so the way into a question like this is actually the third form here, because we're given that the acceleration a is described by minus root x, so minus x to the power of half. And using this first form, what that tells us is that d by dx of a half v squared is minus x to the power of half. So the derivative of a half v squared is minus x to the power of half. What's the opposite of differentiating? Well, that's integration. And we're going to come on to more of this later in the course, but I think it's nice for us to look at it now. Integrating both sides, that means a half v squared is the integral of minus x to the power of half dx. And evaluating that, I would increase the power by 1 and divide by the new power. So the opposite of differentiation. So I would get minus 2/3 x to the power 3 over 2. Increase the power by 1 and divide by the new power. Because it's integration, I also need to put in my plus c. Can I work out the plus c? Yeah, I can, because they've given me initial conditions, v equals 2 when the particle is at the origin. So putting this information in, that means if x equals 0, v equals 2. So substituting in v equals 2 to the left-hand side, 2 squared is 4, divided by 2 is 2. 2 equals 0 plus c, therefore c equals 2. Meaning that a half v squared equals 2 for c minus 2/3 x to the power 3 over 2. Multiplying by 2 and taking the square root, v equals the square root of 4 minus 4/3 x to the power 3 over 2. Whenever I do a square root, just need to be a little bit careful. Do I want the positive root here? They've given me an initial condition, and so yes I do, because if I substitute in x equals 0, I want the answer to be positive 2, not negative 2, so I want root 4, not minus root 4. So this is quite smart. It would have been very difficult for us to do this another way, but because we have this alternative form of acceleration, we can use our related rates and quick bit of integration to get a closed form expression, a neat expression for v in terms of x. So this is just part A of today's work, but I'm going to leave it there. I'm going to do a separate video on the parametric equations. So take a break, have a look at a couple of the questions, and then when you get onto the parametric ones, come back, watch the second video, and we'll go from there.